So detecting unknowns is very challenging, and it must be a constant in your work. So how do you deal with that when you're trying to detect unknowns that change from year to year?
Yeah, so we're really looking for everything that's there as much as we can. So if things are changing, we're just looking at all the unknowns. And so rather than what most people do is they'll have a small group of target analytes they're looking for, maybe 20, maybe 50 target analytes, maybe 5. We look for everything. Every peak that we see by GC mass spectrometry or LC mass spectrometry, we're trying to identify them if we think they're important. Particularly if they have halogens on them, if we can see from the mass spectra they have halogens, we'll try to go after them and try to identify them. And in that respect, high resolution mass spectrometry is very, very important, both with GC mass spec and with LC mass spec. And so we use a lot of high resolution mass spectrometry to uncover these unknowns. And we're always out looking for the most sensitive technique we can find to be able to see low levels, trace levels of these things. It's very challenging, especially when you have trace levels in a very complex mixture with hundreds of things present. You know, it can be very challenging.
And the study of emerging contaminants also includes transformation products, as you were kind of mentioning before, which adds even more complexity. So how do you handle that?
So again, you know, we're not just looking for the parent compounds, we're looking for things they can transform into. So we're looking at all of those peaks, all the GC or LC mass spec peaks. And disinfection byproducts are inherently transformation products of natural organic matter and other contaminants into these DVPs. But then other things, you can have microbial transformations, you can have hydrolysis in rivers and whatnot, and other different kinds of transformations. And so that can be important. And in fact, one of these things we've been looking at are the transformation of X-ray contrast media that are pharmaceuticals used for medical imaging of soft tissues in our bodies, our lungs, our organs, blood vessels. Those are some of the highest pharmaceuticals that are found in environmental waters, and we found that they can transform in drinking water treatment with chlorine or chloramine treatment into some very toxic iodinated DVPs. So there's a classic example of something that was totally safe, used for medical imaging, completely safe, non-toxic, used in high levels, very stable in wastewater treatment, very stable in the environment, transformed into something very toxic that we should be concerned about.
So what do you do? Do you sit there and try to run the transformations that might happen and try to predict what those transformations are to then study those products?
We do that some of the time, yes. Sometimes we'll do controlled lab reactions, and with the disinfectants in particular. So we'll take, in that case, when we were looking at the X-ray contrast media, we took one of those that we found the most often in our drinking water reservoirs. It was iopamidol, and we took and bought a standard of that and reacted it in the laboratory and looked for these same iodinated DVPs that we were seeing in the real world and see if, in fact, it does form. And so we do that in the laboratory, yes. It's an important piece of that, because not just identifying them in the real world environmental samples, but it's important to understand how they're formed, and you do that by doing these controlled reactions in the laboratory.